Welcome to this video on communication systems and signal measurement. We will cover the basic concepts, principles, and quantitative analysis crucial for understanding how information is transferred. We begin with Part 1, Introduction, focusing on the foundational concepts of information transfer. What is communication? It is the fundamental process of exchanging information, ideas, or signals across space or time. In technology, it specifically refers to the reliable transfer of information from a source to a destination. The purpose of communication systems is centered around four key objectives: accuracy, efficiency, reliability, and real-time delivery. These ensure that data is transferred correctly, quickly, robustly, and with minimal delay. The basic communication model includes the source, the transmitter, the medium, and the receiver. This linear chain represents the simplified flow of every electronic communication system.
The information source provides the primary message, which can be acoustic, visual, or data. Transducers convert these physical quantities into electrical signals for communication. Information exists as either analog or digital signals. Analog signals are continuous time, while digital signals use discrete binary values, zeros and ones, offering higher robustness and ease of processing. The role of the transmitter is signal conditioning. The transmitter modifies the source signal to match the medium's characteristics, preparing the data for transmission over long distances. Transmitter functions include encoding, converting data for efficient transmission, modulation, imposing information onto a carrier wave, and amplification, boosting power to overcome resistance. The transmission medium, or the channel, is the physical path connecting the transmitter and receiver. It dictates the maximum data rate and the amount of signal degradation that will occur over distance. We classify the types of medium as wired, guided, using physical conductors like cables, which are secure and stable, and wireless, unguided, using electromagnetic waves for flexible and mobile communication. Signal propagation involves the signal losing energy and changing shape as it travels through a medium. This graph visualizes the signal's attenuation or power loss over distance. A critical challenge in communication is noise, which refers to unwanted disturbances that corrupt the signal and must be mitigated by the system. The receiver performs information extraction, acting as the inverse of the transmitter. It picks up the corrupted signal, detecting weak signals, and intelligently ignores noise to recover the original message. Receiver functions include filtering, which removes unwanted noise, demodulation, stripping away the carrier wave, and decoding, reversing the source encoding to recreate the original user data. The complete system flow involves four main stages: input, encrypt, transmit, and reconstruct. The system is successful if the output signal closely approximates the original input message. We now move to Part 2, Communication Modes, classifying information based on its directionality. Simplex mode is characterized by one-way traffic. Data flows strictly in a single direction, like a one-way street, where one device is only a transmitter and the other only a receiver. A classic simplex example is television broadcast, where a TV station transmits signals to your TV set, but your TV cannot send data back to the station. Keyboards and paging systems also operate in simplex mode. Half-duplex mode allows two-way communication, but not simultaneously. Devices take turns transmitting and receiving, requiring coordination to avoid collisions in the communication channel. Walkie-talkies are a perfect example of half-duplex. Users must press the push-to-talk button to speak and must release it to hear, often using the term over to signal the end of a transmission. Full-duplex mode allows true simultaneous interaction. Data flows in both directions at the same time, enabling both parties to talk and listen without interruption. This is the most efficient mode. Modern telephones are a full-duplex example. You can hear the other person while you are speaking. High-speed mobile networks and internet connections also use full-duplex systems. This table compares the three modes across key parameters, including directionality, simultaneity, channel use, and typical application, highlighting their key differences. Next, we delve into Part 3, Signal Measurement, focusing on the quantitative science of decibels, or dB, essential for analyzing signal power. Signal measurement is crucial for performance auditing, calculating system gains and losses, standardizing component comparisons, and troubleshooting weak signals against the noise floor. The decibel, or dB, is a relative, dimensionless unit that expresses the logarithmic ratio between two values of power or voltage. The logarithmic scale is used because it compresses huge signal ranges into manageable numbers and simplifies complex multiplication of linear gains into simple addition and subtraction. In terms of power ratios, a key rule is that +3 decibels always signifies a doubling of power, while -3 decibels means the power is halved. For voltage ratios, the coefficient in the decibel calculation changes from 10 to 20 because power is proportional to the square of the voltage. Unlike the relative nature of dB, dBm is an absolute unit of power measurement. The m in dBm stands for milliwatt, giving it a fixed reference point. The reference of dBm is fixed at 0 dBm, which is exactly equal to 1 milliwatt of power. This serves as the anchor point for all RF power calculations. In summary, dB is relative and describes a change in signal, such as gain or loss. dBm is absolute and describes the actual power level of a signal. Signal amplification is the process of boosting a signal's strength by adding energy from an external power supply. This is essential for compensating for signal loss over long distances. In decibels, positive dB values represent gain. For example, a 20 decibels gain means the power is increased by a factor of 100. Only active components can provide gain. Signal attenuation is the gradual loss of intensity as a flux travels through a medium. This loss occurs due to absorption, scattering, or distance, decreasing the signal's strength. Attenuation is represented by negative dB values. A -3 decibels loss means half of the signal power has been lost. Passive components like cables always introduce attenuation. In cascaded systems, the use of dB simplifies power analysis. You can simply add and subtract the dB values of each component to find the final power level. A key practical application is link budget analysis. Engineers use these measurements to ensure the received signal is strong enough for decoding, but not so strong that it causes equipment damage. This table shows an example of a system analysis where inputs in dBm and component gain/losses in dB are used to calculate the final power output. To summarize, we covered the flow of communication systems, the 3 communication modes, and the key measurement units, dB for relative ratios and dBm for absolute power. Understanding communication systems and their quantitative measurements is the key to superior design and performance analysis. Thank you for watching this video.